So welcome back. Speaker-wise, we stay in the south of France, this time from Université Côte d'Azur, near Nice, where Stefano Marcantoni will give a talk. Please.
Thank you, and thanks to the organizer for this opportunity to present my work here. And I apologize because I'm not going to talk about quantum trajectories, but the topic is anyway open quantum systems, so possibly it will be interesting for you. I want to emphasize that this work has been done in collaboration with Marco Merkli, who is now at Memorial University in St. John's in Canada. My plan is this one, so I will first give you a brief introduction to the model and to the notation I will use, because it's somewhat unusual for, at least for the physics literature. And then I will present the results, then I will give you a simple example, and if time permits, I will also present some little ideas on how to prove these kind of results. So let me start with some basic background. So I'm considering here the usual open quantum system setting, which is we have a small system S, which is the system we are interested in, which is interacting with a reservoir that in this talk I will consider like a proper reservoir, so it's something that we cannot control at all. So this is different with respect to many talks that we have heard in this conference. And so what one can do is to trace away the degrees of freedom of the reservoir to find the reduced dynamics of the system S alone. But this dynamics is usually very complicated, and we lack, we have very few exact solutions for those. And so the strategy is to find effective dynamics for the system S alone that capture the relevant physics in suitable scaling regimes. And possibly we would like to do this in a mathematically rigorous way. So I put here, of course, this was done previously in the literature in many different scaling regimes. I put here just a few examples that are basic textbook example you can find in textbooks. So we have the singular coupling limit, the low density limit, and maybe the most famous one is this weak coupling limit, which was first studied rigorously by Davis in the 70s, and it was recently refined by Merkli, who gave uniform in time bounds on the goodness of the approximation. And in this work, we will study yet another limit, which is the limit of strong coupling, and in particular of infinite coupling. If you're interested in the details, I advertised this archive paper that was published recently. Okay, so let's be more concrete about the model. So I'm considering here a finite level quantum system, which is our system S, interacting with a reservoir, which for me is a reservoir composed of infinitely many bosonic modes. And you see here, so the Hamiltonian for the reservoir is this continuous integral of course, this A and A dagger, as usual, are the canonical, are the bosonic creation and annihilation operators, obeying the canonical commutation relations. And we have here this special relation omega k, which you can think of as being a modulus of k or even k squared. It's not really very relevant for the next, for what I will tell you in the following. We have this interaction Hamiltonian, where G here is just a matrix, is an operator on the Hilbert space of the system S. And I emphasize here the spectral decomposition of this operator G, because it will be very relevant for what I will tell you later. So this PL will be the spectral projections, not necessarily rank 1. So you can have degeneracies, and this will appear in the results. And here we consider this phi of g, which is called the field operator, which is basically a linear combination of A and A dagger with some complex valued function, g of k, which is in L2. And this is called the form factor. Okay, so we would like to describe states of this composite system, and in particular, we would like to describe states of the reservoir. So we can think of thermal states at invert temperature beta. The point is that when dealing with infinite systems, one has to be careful because, as we have seen before, HR has a continuous spectrum, and this means that the operator e to the minus beta HR, despite being well-defined as a bounded operator, is not trace class. So if you remember yesterday's lecture about norms, this means that the operator norm is finite, but the trace norm is infinite. So it cannot be normalized. And for this, we are using what is the so-called algebraic approach, which is, okay, I put here a reference to the book of Brattelli-Robinson, which is the standard reference. Basically, what we do is we consider the algebra of observables of the reservoir in this case, but it will be the same for system and reservoir together. And so in the thermodynamic limit, states are described by means of the expectation values of these observables, because these expectation values are well defined in the thermodynamic limit. So you can build the theory based on these, you can describe states by means of positive linear functionals on the algebra of observables, which for us are just the expectation values of the observables. And in particular, since we are dealing with a bosonic algebra, basically what we need to know is the expectation value of this operator W, which is the Weil operator, defined as the exponential of I, the field operator that I was showing you before. So the linear combination of A and A star. Yeah? This is just if you want my assumption. So I'm describing my thermal reservoir as something which has infinitely many modes, and this, of course, since I'm considering here a continuous dispersion relation, this gives me a continuous spectrum for this operator. If you want, this my way of modeling the reservoir. It would be different if I had a finite number of bosonic operators labeled by k, discrete k, finite. This would be different. So I could define in that case the density matrix in the usual way. But in this case, this is not possible. So in order for e to the minus beta HR to be trace class, I would need a discrete spectrum for pure point spectrum for HR. Yeah, this is just a result in mathematical theory of operator. So, yeah, I was telling you that in the bosonic case, what we need to know is the expectation of this Weil operator, because then by taking derivatives, you can reconstruct all the possible correlation functions. So this is also called the characteristic function of the state. And in particular, for the example I was showing you before of the thermal state, this is the explicit expression for the characteristic function. So you see here all the parameters that were already introduced before, and the scalar product is the scalar product in L2, of course, because this f is a function in L2. And we are assuming, as usual, the initial system reservoir state to be factorized. So now I will use this notation of the omega. This will always be for me some expectation functional on the observable, in this case of system and reservoir together. And we are interested in studying the system density matrix in the ultra strong coupling limit, which means for any matrix A, basically any matrix D by D matrix A, we want to compute the evolution, the expectation of the evolution given by the total Hamiltonian, and then take the limit for the modulus of lambda, which is the coupling constant, that goes to infinity. And you can map this to the elements of the density matrix of the system, which is well defined because S is finite. We can call this rho S of t. Okay, so we are ready to see the first result. There is a technical condition on the form factor, which is not very relevant, I would say. It's just, technical condition to prove the theorem. But the point is that under this mild condition on the form factor, we can show that for any t greater than 0, the system density matrix in the ultra strong coupling limit is given by this expression, where you can recognize a non-selective measurement where the PL I showed you before, these are the eigenprojections of the coupling operator G. And you have a unitary evolution with this Zeno Hamiltonian, which of course reminds you of the physics of the quantum Zeno effect, which is obtained from the original Hamiltonian HS, again projected onto the say eigenbasis of the coupling operator G. So what does this describe? This describes a dynamics where you have a block diagonal structure of your density matrix, where the blocks are defined by, again, by this PL. And inside of so all these blocks, you cannot have transition between the different blocks. And inside each block, you can have evolution, a residual unitary evolution given by this Hamiltonian. So, of course, this is true. I mean, there are trivial cases. Of course, if there is no degeneracy in G, which means that all the PL are rank 1, then the dynamics is sort of trivial in the sense that you don't have this unitary evolution because, all the density matrix will be really diagonal, so there's no possibility to further oscillate. And again, in order to have a non-trivial evolution, it is necessary that at least one of the PL is multidimensional. And again, there should be some condition on the HS, because if HS is still completely degenerate in that subspace, again, it would be like, you have a phase, here which is completely eaten out by this other phase, contrary phase. So you wouldn't see any relevant evolution. Okay, and this, of course, as I was telling you, and probably you also imagine it, this is exactly the same dynamics that you obtain the usual setting for the quantum Zeno effect, which is, okay, you imagine to have a unitary evolution interspersed by projective measurement on some basis that you choose. Here, the basis is given by the coupling operator G. And then you will find in the limit of, say, infinite measurement in finite time, you will find exactly the very same evolution. Okay, we have actually a further result. Because in principle, so this framework is completely general. So in principle, you could ask also what happens to reservoir observables. And in this case, okay, the theorem is written in a way that is a bit complicated, but the point is that If you just consider reservoir observable, the limit is not well defined. So you will have some terms that oscillate very wildly with lambda, for large lambda. So in order to get a well-defined limit, one has to dress this observable of the reservoir with some system observable that somehow can counteract with some lambda-dependent system observable that can counteract these very wildly oscillating phases. Okay, I will not enter into the details here. And a further generalization, which is probably more interesting, is that you can do the same if you have the system connected to different reservoirs. And okay, in this case, morally, you could see the S plus, say we want to take the strong coupling just in L2. And so morally, you could see S plus R1 as, system S prime. And everything, you would expect everything to work exactly in the same way. And in fact, it is so, but the point is that now the Hamiltonian of S prime would be unbounded, because now you have a proper reservoir that you are considering as your system. And therefore, we need some technical condition on the state of R1 in order so that everything converges and we have a well-defined theory for it. But morally, you could say that the result is what you would expect, which is this one. So essentially, you get the same result for the system S and R1 after tracing out R2. And with the Zeno Hamiltonian, where now the projection of PL are always the projection of the coupling operator of the system. So we always consider the projections of this G2. And this is the relevant Zeno Hamiltonian in this setting. And this, in a sense, is more interesting because then, in the other case, you can only have unitary oscillation inside the different blocks. In this case, if you then trace out also the other reservoir, the reservoir R1, you can have a dynamics for the system S alone, which is quite rich. And in particular, you can also find non-Markovian effects. So this is a very simple example. You can consider two qubits interacting with these two reservoirs. Consider the coupling G2 as this very, very trivial, I would say, coupling with sigma z. So each of the two qubits is coupled independently through sigma z. And this means that the spectral projection of G2 are, of course, what you can see here, and it's very simple to see this. And the important point is that we have P0, which is a rank 2, so we can expect some non-trivial dynamics to happen in this subspace, two-dimensional subspace, which for us will be like an effective qubit. So you can prepare your initial density matrix just in this two-dimensional subspace. And then by choosing appropriately HS and G1, you can recover the usual pure dephasing model for qubits that you can find also in textbooks. And the point is that everything is completely explicit, and you can find this decoherence function d of beta, which is basically just you see the evolution of the diagonal part. There is a phase, and then there is some d of t, which in the Markovian case, you would expect this to be just some exponential decay. But in general, you have this completely explicit expression. And it was already studied in the literature that when d of t is not monotonic in time, you can have non-Markovianity in the sense of the so-called lack of CP divisibility. So we have heard about this in one of the talks in the first week. So I will not comment a lot on this, but if you have questions, we can come back to this later. Okay, so maybe, yes, I think I can give you also some hints on how you can prove this. So basically, okay, the very short explanation is that we used the Dyson series expansion. We proved that it is possible to exchange the limit with the series and the limit with the multiple integration that you have in each term of the series. Take the limit explicitly for each term, and then do the integration and resum the series. So that's the very basic story for the proof. More in detail, it goes like this. So we define this operator K as the sum of the free reservoir Hamiltonian plus the coupling with the system, and then use Dyson series to rewrite e to the ith in terms of this e to the itk, basically. And in doing this, of course, as you know very well, you will have this series of multiple integrals, and in each term you have a product of dressed Hamiltonian HS with this evolution e to the itk. So this is the expression that we would like to compute. So this is the evolution of a generic observable of the system under the total Hamiltonian. And then in the end, we would like to take the limit lambda, modulus of lambda to infinity. And we substitute the Dyson series representation so that we have 4 terms. The first term is the simplest one because, in fact, you don't have the series, you just have the evolution with this Hamiltonian, effective Hamiltonian K. So maybe we can start with T1, which is the simplest one. So by playing a little bit with the bosonic algebra, we can rewrite this expression as a sum over all possible projection PL and PR on the system part, a phase which will depend on FL. I define it here. So there is the lambda, the coupling constant is inside these functions FL, where you see lambda and also the gamma L, which are the eigenvalues of the operator G. So you see the eigenvalues here and the eigenprojections appear here. And then there is a while operator, which again contains the dependence on lambda. So this is just say an exact calculation that you can do by just exploiting the properties of the bosonic algebra, or properties of while operators and how they interact with say with the operators of the type e to the minus et hr. And therefore, when taking the expectation, we can easily see that you can easily say isolate the system part, and then there is again this phase which will depend on lambda squared, and there is this expectation of the while operator in the state of the reservoir. And this will be very important because now for this, depending on the state that we choose for the reservoir, we have an explicit, completely explicit expression. And in particular, this will be some exponential which decays with lambda squared. And you see here an L2 norm of some function, which, I mean, seems complicated, but it's not so complicated in the end. The C here is because I'm now considering a state which is more generic Gaussian than just the thermal state, but you can imagine here to put hyperbolic cotangent of beta omega alpha, and this would be exactly the thermal state case. So in the limit lambda to infinity, you can easily see that this decays, unless the expression in the exponent vanishes. And in that case, it would be 1. I mean, here maybe it's a bit, I mean, it's quite simple to see that in order this to vanish, it means that the function inside is the function identically 0, because this is the only way the norm can vanish. And this selects basically the case L equal R. So you're basically saying that if you go to the previous expression, when you take the sum, you're just selecting, so all the terms are 0 apart from those where you have the same projections on the left and on the right. Okay. And now we look at the other terms in the same way. So morally, it works exactly like this. The point is that everything will be more complicated because we will have functions like this, but which are, say, are much more complicated because they include terms with many different times, many different, say, gamma to indices, which depend on the fact that in each term of the series, you have multiple integrals to do. And in fact, this is how you can write the term T2, for instance. And so as I was saying, the general structure is quite similar. You will use again this property that I indicate here with the triangle, which was, I remember you, this property here. So you can rewrite the expression in a way that is more convenient for the proof. And then you will have, for any of those HS terms, you will have a while operator that appears. You can combine them all because of the while algebra. And this is more or less the expression that you get in the end. So you see you have many different, summation over many different indices, multiple integrations. You have a phase that I put here just like phi of lambda, which is indeed very complicated as an expression, but everything is explicit. And you will have this expectation of over the system observables and expectation over the reservoir part. And again, you will do exactly the same thing. The only point, as I was saying, is that now the function eta, I mean, I don't write it explicitly. There is an explicit expression, but it's very complicated. And if you remember the technical condition on the G that I was mentioning, on the form factor that I was mentioning when stating the theorem, that condition is just to ensure that this norm here vanishes exactly only in those cases when all the projections coincide. So you have the very same effect. Of course, in those cases, when all the projections coincide, you will have, so you could do exactly the same thing and you will have what you expect, but of course you have to prove that these are the only cases where in fact the exponent vanishes. And this is a bit of the, say, technical part. But in fact, I mean, I would say as a, say, the idea of the proof and the logic of all the steps is quite elementary. It's just that, you know, you have to do a lot of computations and then check a bit of things, but there's nothing really sophisticated about it. And so then at this point, remember that now we have a series and a multiple integral, and we want to take the limit lambda to infinity. So in principle, we should take the limit after doing all these other operations. But in fact, since one can show that the Dyson series converges uniformly in lambda, we can exchange the limit with the series. And then by means of the dominated convergence theorem, we can also exchange lambda, the limit with the multiple integration. So in the end, we are just taking the limit term by term, as in the previous case. And then this, again, selects the case where, the unique case where all the projections are in fact equal. And is good to emphasize that in this case also this phase that in principle could spoil the result in fact vanishes when all the projections are equal. This you can see by looking at the explicit expression, which I'm not writing here because it's a bit complicated. Okay, I think yes. Also, then of course you can do the same for T3 and T4. And the last point, once you have the limits done for all the possible terms, you manage to quite easily, I would say, to do the integration and resum the series. And in fact, the final result is exactly what I was mentioning in the when stating the main theorems. So this was, of course, for the theorem T1. Then for the others, you have, again, a little bit of technical details to look at, because in the case of two reservoirs, as I was telling you, the Hamiltonian is no longer bounded, so one has to take care of that. But the logic is exactly the same. So I think I can conclude now. So we computed the reduced dynamics of an open quantum system in the ultra-strong coupling limit. And we have shown that it consists of a non-selective measurement onto the eigenbasis of the coupling G, and then a unitary evolution with an effective zero Hamiltonian. And we generalized this to the case of two reservoirs when one of the two couplings is sent to infinity and the other one stays finite. And in this case, the reduced dynamics of the system alone can be much richer and also non-Markovian. And of course, there are many questions open again, because this is just the result in the limit. So physically, you will have lambda which is large but finite. So, well, the first thing would be to find the explicit bound on how good the approximation is, which now, of course, we have bounds, but they are bounds for term by term. So we should extract those bounds from the multiple integration and from the series in order to have a global bound on how good the approximation will be. And of course, it would be nice also to have corrections to this lambda, to this Zeno effect for finite lambda, where you can really see some proper dissipative evolution. And maybe a shortcut for this would be to, for the moment, just also try to find a time rescaling such that you can slow down the initial non-selective measurement and see in finite time how these off-diagonal blocks decay. And this, I mean, we are working on this at the moment, and we already have some preliminary result, but okay. I will tell you about this probably another time. So thanks for the attention.
Questions to this talk? Yes, please.
So thanks for the talk. So I understand then that essentially the dynamics is Markovian, at least for the case of one reservoir, for all positive times?
Yes, so it is Markovian in a trivial sense, in a way, because, is at first you have just this instantaneous projective measurement, then it's unitary. Yes.
But then it's essentially isentropic as well. So in some sense,
yes.
beyond this
you have a loss. The entropy will change at when doing the measurement. So in the
exactly.
instant t0, but then it will be isentropic. Yes.
Then yeah. Okay, good. Can you say anything about elaborate a bit on the prospects of maybe finding 1 over lambda corrections? So.
I cannot tell you very much. So as I was saying, what we are trying to do now is to say cheat a little bit and find a scaling limit for the time. So rescale time in such a way that we can see on a rescale time scale, we can see this initial projective measurement happening on a time interval, and this will allow somehow to resolve the initial process that causes the change in.
There were some results by Larry Sullman comparing quantum xenodynamics under continuous Hamiltonian, and sequence of projective measurements. I wonder whether that could help. So
maybe. We'll look at that.
So you choose some initial condition, and if I understand correctly, you separate with the initial condition of the system and the bath, they are product states. Is that correct?
Yes.
And
yes.
so then the question is, in the strong coupling limit, if you prepare the system together, then the equilibrium the starting point will be different. So is this in your mind, or can you say something?
Yes, I see the point. So I think we should be able to say something also, say for non-product states, because in the end, yeah, I guess we can see something. We can say something also for non-product states, because in the end, what we will need is that, okay, imagine that this now is like a convex combination of terms like this, of states like this. Okay, but this would be separable anyway. Yeah, okay, I cannot tell you now that we are able to generalize everything for example, for entangled initial states. But yeah, that's certainly something to look at, because yeah, as you say, when you have strong coupling, it's not very reasonable to have a factorized initial condition. I agree with that.
Further questions? Yes.
Last, yeah.
Thanks. Merci. What happens if lambda 1 and lambda 2 are finite?
Lambda 1 and lambda 2 are?
Finite.
If they are finite, then, I mean, you have a very complicated open quantum system with two reservoirs, and I mean, I don't know what you can say in general.
But normally, this is the context of the Fourier law. No? Or maybe you have two baths?
Yes.
And you want to prove the hydrodynamic limits in this setup, no?
Well, here the thermodynamic limit is somehow assumed from the beginning. You know, this state omega r is already in the thermodynamic limit. So, of course, I could, I mean, I could define, of course, this state is perfectly defined, well defined. But the point is that then I mean, if you wanna compute something after evolving with you know, with the total Hamiltonian, which will couple everything here, in general, I mean, I don't know what you can say. I mean, that's why we use scaling limits, because in general we cannot say very much. So we look at the specific. But of course, so the thermodynamic limit here is already done. Is the starting point in a sense, because it's what you use to get this kind of expression for the characteristic function. This already.
Thank you very much.